today on Hugging Face. So this is basically me 5 minutes going through the dataset view on Hugging Face. You still see these very weird examples where it's really not clear if this is what you want to train your model on. And another example from the literature are near duplicates. So exact duplicates is easy to filter, but near duplicates where substrings of a document are fairly similar is a bit more tricky and a bit more expensive to run. And if you, for example, try to deduplicate, including near duplicates, this usually increases the performance a lot, especially on downstream task datasets like LM1B and Wiki40B. And in my own work, I looked into, for example, the Pile, which is another pre-training corpus. It's a bit more diverse by design than C4, and you have similar issues. Like you have these, even after clustering or even after filtering heuristics, you have these examples and data points that are at least not obvious helpful for downstream tasks people usually consider. And another issue is that the mixture proportion of different corpora is not so obvious to get as well, or is not so obvious either. So if you look at common and like prominent language models, you can see that they often have different mixture proportions. They have different sources of data they are trained on. And weighting them is still, I would say, fairly like greenfield. So if you consider, for example, the Pile with 22 subsets, this effectively introduces 22 hyperparameters, and running a pre-training run with a different configuration of these is obviously very expensive. Another issue is also that these are clusterings based on a data source, but data sources might not be, or like the attribute a data source might not be that informative. Like you can have semantic overlaps across different data sources. What you really care about is maybe more the topic of a particular cluster. So if you look, for example, at the Pile paper, they argued that choosing these proportions by hand is good enough. So they argued that, for example, academic texts should be upweighted and are more higher quality. And so they ended up having these hand-chosen domain weights. But more recently, there's a cool paper that tries to learn these. So they try to learn this by first training a smaller reference model with uniform weights, then training another model, a proxy model, where you want to take into account the performances of that reference model you trained before, and then through a minimax game, try to improve the headroom for the model to improve. So basically the difference between the reference model and the newly learned model should be minimized. And you can then get these domain weights. And interestingly, even though by necessity, by like learning these domain weights, you, in comparison to the uniform one, would downweight a few domains, overall this still improves the downstream performance on all test sets. A question here to the audience. So if you're familiar with some of these pre-training corpora, are there any where you would think that these should be maybe up or down weighted if you consider the original reference weights here on the left column on the baseline? So basically what happens here is these are like on the holdout shape here that I will reveal in a second. You will see the newly found weights for each domain subset of the Pile. Does anyone here have like some intuition of which of these subsets might be up or down weighted in order to have like a good data set that forms on test data from the Pile or like general language model data sets? Yes.
I'd be interested to know whether GitHub was important for a general language model versus, say, Codex and reasoning tasks.
Yeah. So I think they try here to optimize for all test sets of all domains, so not just coding. But so you are interested whether the coding subset here was changed or not. Is that right? Do you have an intuition of whether it was or not? Assuming you want to improve over all domains on average?
It looks like it was dialed down.
So you think it got dialed down? Okay, yeah. We will reveal in a second. Anyone else? Any other suspicions? Yes.
Just wonder if The subtitles might contain some gold that should be upweighted a bit.
YouTube yes. Okay. Cool. So YouTube subtitles upweighted. Okay, I remember that. Okay. Any other prediction? Yeah.
Upweight Hacker News.
You would upweight Hacker News. Okay. Cool. Why?
Unusually civilized comments, I think.
Cool. Okay. Cool. Nice. Anyone else? Yes.
Anyone emailed?
Anyone email up or down? Up. Okay.
And it was written in actual English.
Okay. Yeah. I think these were emails from the Enron scandal. I forgot why they even included that, but yeah. Okay.
They had to be released for the court filings. They were put in the public domain for the court proceedings during the bankruptcy. That's why they're in the public domain.
Oh, right. Okay. No, I meant like why they included it in the file. Like in general, yeah, that's a fair point. But yeah, why is it relevant for language? But okay, never mind. Yeah.
So just what's the evaluation procedure for this then? The test data set on which they, as I understand, evaluated and found the better reweighing.
So the evaluation is basically the average performance test sets of all domains, across all domains.
Equally weighted.
Yes, the test set I think is equally weighted. Yeah. Okay, maybe let's reveal this in the interest of time. So Hacker News got upvoted. Subtitles got upvoted as well. Enron emails got upvoted as well. Wow, so many good predictions here. Yes, we will come back to this slide in a second. Another POPs quiz. So this is, here we see a plot of HelloSwag, which is like a fairly common and somewhat more robust evaluation downstream task. Disclaimer, like people are complaining about evals a lot and there's no like one, canonical downstream evaluation data set that is perfect. But assuming this one is fairly okay, what do you think, which of these pre-training corpora could correspond to which line here? Like, does anyone have some intuition? You don't have to give like a perfect ranking, but maybe just like, maybe see like, where would you see C4? Where would you see the pile? Where would you see Llama mix? Anyone have some clue or none at all? Yes.
HelloSwag is in English, so I don't expect to see much improvement by training multilingual. So
that's a good point. Yeah, that's a good comment. Any other comments?
The pile is the blue line.
The pile is the blue line, right? Okay, why do you think so?
Because it had the highest weighting on the previous slide.
Okay, sorry, but so on the previous slide, these were subsets of the whole pile. And so pile CC is like their specific common crawl subset.
Mosaic mix will be blue.
Okay, Mosaic is the blue, yeah. Okay, I will expose this. So interestingly, C4, which is just web data, and which is, I think, the oldest of these corpora, is still by far most competitive. And I think this begs the question, is web data all we need? There is another paper that made similar observations where they just figured out new cleaning heuristics for common crawl data that then outperformed much more diverse data sets. I mean, diverse in terms of data source. And if we go back to these weights, we see something similar here again, where actually pile CC, which is again like a common crawl subset, was upweighted a lot. Sorry. Okay, cool. Yeah. Next challenge, high pre-training costs. I think someone already said it in the audience. So lots of you probably have seen the scaling law papers. I think one interpretation might be that scaling or improving performance in terms of compute is really unsustainable. I mean, this is somewhat of a value judgment here, but basically, if you interpret these log-log plots in a way that, like, how much do you have to increase compute to decrease the test loss, you can see that you basically have to put in orders of magnitudes more compute to just reduce the error, relatively speaking, by a few percentage points. And so how are we going to deal with this? One area of work are compute optimal training recipes, which we will discuss in a second. So basically, can we scale the model and dataset size more optimally given a fixed budget? Other considerations are which pre-training objectives might be the right ones for our use case. There are various tricks that are somewhat independent or agnostic to the learning task. Yeah, we will discuss these as well in a second. And then, of course, there are hardware level optimizations, which don't really care about it, like the task to be learned at all, which are really more about how do you perform parallelism, for example, across accelerators in a way that you reduce communication overhead, or can you fuse certain operations so that there is there's less memory reading and loading and time spent on this. So the compute optimal scaling line of work, I think, started with the Kaplan paper we already saw. A bit later, there was the Chinchilla paper by DeepMind, also got lots of attention. And they basically argue that you can scale more efficiently by new scaling laws they derived. And basically, they argued, for example, that compared to their previous work where they trained Gopher with 280B, you can, for the same compute training budget, reach a much better performance if you train a smaller model, the 70B Chinchilla, but four times more data. Since maybe you may be interested in applications where you don't have unlimited data, the question arises, okay, what do we do when we have limited data and we want to repeat the data? So this great new paper called Scaling Data Constrained Language Models talks about repeated data, and when basically a point in time is reached where you have diminishing returns and repeating the data over and over is not worth it anymore. And I think this is pretty interesting. Here on the right plot, on the right plot, you can see the blue dashed line where, given a fixed compute budget here, these amount of flops, how to set the number of epochs or number of tokens, even when you repeat tokens, such that you get a slower or a lower loss. On the pre-training side, or like on the objective side for pre-training, there are several ideas, mostly designed for different applications of the model, or like downstream usage of the model. So, for example, if you really care about best zero-shot generalization, it has been shown that causal decoder models pre-trained with the standard next token prediction objective work pretty well. But if you care, for example, about a model that performs well after multitask fine-tuning, and this could be, for example, your industry-specific fine-tuning task or fine-tuning tasks, then encoder-decoder models trained with span corruption, where you don't predict a whole sequence of tokens that is contiguous, but you sample these random spans across your data point, can work better. There's also a cool idea called Meet in the Middle that is rather new. I think it came out a few months by Microsoft. And they argue that you can actually improve over next token prediction and also increase the capabilities of infilling, which is, for example, relevant if you write Julia code, by having two-sided objective. So basically you have one model, but you compute the forward pass in two directions. So first from left to right, and then from right to left, and then you predict one token in the middle, and then you try to decrease the distance between the log probabilities of each of these forward passes. Pretty cool idea. I haven't seen much usage of that yet, but yeah, they claim it's a more efficient use of data. Another cool finding of this paper I just mentioned here is that you can also pre-train on one combination of masking strategy and pre-training objective, and then just fine-tune on a different one. So for example, if you, on the left-hand side, first pre-train with a masked language model objective, a non-causal decoder-only model, you can then fine-tune this towards causal full language modeling. So full language modeling just meaning next token prediction. And you outperform a model that was trained from scratch on causal FLM by a lot. I think this is pretty cool because on Hugging Face we have so many pre-trained models that we can just download for free. So yeah, I think this is a pretty impressive result.
John, will you be making the slides available?
Yes. Yes.
Could you just
Yeah.
One more. Yeah. So just again describe what is the orange and green here. So causal MLM is the pre-trained, generally like the autoregressive model, right? So do they adapt it using non-causal objective?
On the right-hand side, it's vice versa. So yes, you adapt a causal decoder only model with full language modeling into a non-causal decoder model with MLM objective.
Right. And then the green one is MLM adapted. So the after
That's the green one I just described, I think.
oh, that's a green model.
Yes.
So what's the orange? Oh, the orange is like basically mask language modeling, and the blue one is the autoregressive model, and then the green is you take the autoregressive model and adapt it using mask language modeling.
Yes, I think so. So the green one, yes. And the blue and orange one, yes, I think you're correct. Yeah.
And so, okay, interesting. And what is and the loss here? Is it the loss of that objective? Or?
Yes, the target objective. Yeah.
Okay, thank you.
Yeah. Whereas maybe this was a bit fast or a bit rushed, but yeah. Yeah, I guess the reason why I find this exciting is because to me it would have seemed that you would need to pre-train from scratch if you care about a whole different objective. So for example, masked language modeling is good for embedding models. So I would have assumed you just have to train a new embedding model from scratch. But it seems that you don't have to, at least in these settings, this paper considered.
And on the left, LM adapted non-causal MLM is basically the opposite way.
Yeah.
Take the like BERT and adapt it using generative, autoregressive objective. Is that the idea?
I think so, yeah. Convert non-causal decoder only model pre-trained with MLM. So BERT is an encoder model. So it's not exactly BERT, but it's the same training objective like BERT. And yes, and then so besides the architecture, yes, exactly.
Are there some thoughts about why it works? What's going on?
Yeah, good question. I mean, I think it's better. I think it's a good idea to read this paper more carefully to dig into why. But if you hold the corpus fixed, I would assume that, I mean, it would be, on one hand, I think it would be surprising if you can't transfer that knowledge at all, right? Because, so if you look here, like, overall, the corpus might still be the same. It's just, how do you set the inputs and outputs, or how do you define the inputs and outputs that changes, and then the attention masks that are changed. But yeah, I mean, I should not talk too much about why. It's better if you look into the paper. Cool. There's another big line of work on efficient architectures, which try to save computations. This also, of course, holds for inference. But because here we talk about pre-training costs, I want to highlight that some work found that some of these really underperform the vanilla transformer. And I think on Twitter, you basically once a month or so, you see a discussion on like, why do we actually still need a transformer? Why does the 2017 transformer work so well still, and so on? And I guess my understanding of the literature would be people tried really hard to replace the vanilla transformer with lots of different things. And if you see a new paper like claiming they came up, for example, with an efficient attention mechanism, their results, yes, usually show that it works. But then replication studies like this often don't really replicate these results. And therefore, my feeling is that this is still a bit undecided, what the best architecture is to decrease pre-training costs. So here, basically, yeah, I think the figure is self-explanatory. You see that as different scales, yes.
Good.
Yes. Yes. Up is the superglue accuracy. So superglue is like a downstream set of data sets. This is one of my works. So in our lab, we looked into other tricks that reduce training costs for pre-training. We did not have the compute to compete with really big labs. So we train somewhat, like these days, probably considered small models, small language models. But yeah, we also found that, unfortunately, if you compare with a strong baseline that doesn't really apply any tricks, yeah, you don't often get a better performance. So layer stacking, one method where you start training with a smaller model. So for example, assuming your target model layer, like the target number of layers that your final model should have is, let's say, 16. The idea of layer stacking is you start with something like 4 for the first quarter of pre-training. You then replicate the weights from the layers. You literally copy paste them and you stack them. You do this, you then continue pre-training, then you do this one more time, and then you go from 4 to 8 to 16 layers. And that, in our experiments, helped a little bit, especially for smaller budgets, but not a lot when you increase the budget. And especially for the biggest budget we considered, no method really beats the baseline. Just check the time. I think I have to go a bit faster, but yeah.
You're pretty, don't worry about time. I think we have time, you know, we started late, so it's fine. Just a wider question here. How robust is it to do these kind of experiments on slightly smaller models, like you say, and then try and apply the learnings to larger models? Just like, it's a broad question, but if you have any thoughts on that, really appreciate it.
Yeah, I think I can't give any guarantees. That would not be very honest, but I think based on papers like, for example, this one, it often seems that many findings do scale across scale. Many findings do scale across scale. Yeah. So yeah, I think to be 100% sure, you would need to try. And then there's like, you know, debates about, are there actually emergent abilities, or is this more like a phenomenon based on the wrong way to measure downstream performances? But I don't want to go into this debate now, but like basically, I can't 100% guarantee that it will scale, but given that we scale, for example, for 3 different budgets from 6 to 12 to 24 hours already, and papers like this, I would tend towards thinking it will scale, or there's no reason why when you scale up, things will look totally differently.
So there's no sense in which there's a certain threshold which you need to get over in order to, you know, say something useful for the really large models?
I think for pre-training, I mean, there is this theory on like these outlier features that you get with a certain model size. I guess this could happen, but I would think it might not. Like I would guess it will not, but I can't guarantee it. Basically, yeah. So some of these methods, for example, we considered here, were also considered, or were also designed for smaller scale cases, where you don't have this critical threshold and then everything changes. Yeah, high inference latency. We heard this already by someone. We argue it's mostly due to 3 reasons, and the first one is probably trivial. So, you know, like larger models require you to do really large matrix multiplications. So that takes some time. Maybe one more interesting one is that autoregressive models require you to decode 1 token at a time. And we will look in a bit we will look into ways to improve that, or to improve the latency here. And I guess a third reason why inference can be very slow is because you have large memory footprints. For example, you have to store the parameters in the KV cache, which we will discuss in a bit, and then perhaps other things the memory occupies. And these large memory footprints hinder you to use larger batches, and therefore you have to load data into memory more often than you would want, perhaps, to increase the utilization of your accelerator, and that slows down the inference. So one way to make models smaller and still have the same or similar performances is knowledge distillation. This is a fairly old idea, I think fairly often used. I won't go too much into this. Mixture of experts is a somewhat new idea. You try to split the model into dense parts that you can then distribute across different accelerators. And then for inference time tokens, you can route them to accelerators such that you effectively utilize your GPUs more efficiently. Another perhaps more banal thing you could do is just to compute everything in lower numerical precision. So especially with the new H100 architecture, they did a great job, NVIDIA did a great job on making lower precision very fast. So for example, I think one cool idea could be to just try and train, for example, a model in int8, which I think I haven't seen so far. It might be a bit tricky, but this would be much faster in theory. And then I guess based on scaling laws, another implication of this line of work is that, well, you could just amortize inference cost by paying upfront a much higher training cost. So ignoring kind of scaling law, scaling, and just throw as much compute as you have on like a fixed model size. And I think this is to some degree what the Llama line of work did. So I think I read that the Llama scaling is not exactly chinchilla scaling, but obviously for us it's great. We can download these models and have much better performance given our smaller inference budgets. Another idea for reducing inference latency is to consider the following. So if you think about how self-attention works, you usually have your query metrics, your key metrics, you do the dot product, you multiply with the vectors of values, you get your attention scores. However, if you do this during inference, because you have to predict the token and then put that token back in, and then do this whole thing again, you actually end up predicting and computing lots of attention scores that are not relevant anymore on a per token prediction basis. So for example, if you look at the product here, there are some sub-slices of these metrics that are already computed in the previous step. There are some that actually we don't care about because we do next token prediction. And so we have a causal masking. And so we really don't care about some of these attention scores if we, for example, want to predict the fourth token at t equals 4. We don't care anymore about the attention score for the first, second, and third token. So the idea of a KV cache, and by the way, I use these great slides by Umar Jamil. The idea of a KV cache is that you just cache the keys and value vectors. So if you predict, for example, the second token, you still keep the key and value of the first token in memory. And then you have less memory loading. You have to have you compute basically this attention score much faster. But the downside of this is that you have to store these keys and values. And depending on the sequence length and the nature of data point that you feed in, this can be somewhat unpredictable. It can be unpredictable how many, for example, keys and values you want to store in the memory. And so if you have a naive implementation of this, your memory system will be very fragmented and reserve lots of memory in contiguous blocks for future tokens. And so this paper that we will, this paper which proposed paged attention, which we will look into on the next slide, showed that for these previous inference latency decreasing methods on the GPU, there's still lots of fragmentation and reservation of contiguous memory blocks that are unused. And this limits the batch size and therefore the throughput that you can use. It's basically a waste of memory. And so they came up with something fairly clever. I'm not sure why it starts at step 4. Now it's step 1 as of 0. So basically you first allocate, basically the idea is that similar to in operating systems in computer science, you want to decouple the physical and logical memory for your inference. So you kind of have like a virtual or logical KV cache block, which does not need to store each KV for each token contiguously, as it's done usually naively. And so the idea is that you put in, for example, the input and the keys and values in the logical block, you generate the next one, and then you have this map from the logical to the physical one, where in the physical one, you can now allocate them just non-contiguously. And this more dynamic memory allocation allows you to increase the batch size and thereby the throughput, because your GPU is more busy with actually running the matrix multiplications than moving data back and forth. And so I tried this literally last week and I was mind blown. So the throughput increases are really crazy. And like in our case, it just worked off the shelf. Like you install this package, you import this code, and it just gives you a huge increase in throughput. The method is called page attention, but the library is called VLLM. Another idea that people have been started using recently is, well, if we consider multi-head attention, we still have to load repeatedly keys and values for each head during inference into memory. And a paper by Noam Shazir from 2019 argued, well, actually, if you just share keys and values across all attention heads, and so basically you keep them in memory, and you only reload the query vectors individually during inference, that makes things much faster and degrades the quality only a little bit. It is a strict worsening of the performance, but it's a cost you might be willing to pay. A cool compromise that was proposed recently and also I think immediately adopted in the Llama 2 paper is grouped query attention. So this is a paper by Ainsley et al. I think it's a Google paper. And here the Llama 2 paper basically shows that in a similar vein, because you can now scale up the batch size by a lot, and you can fit much more data on your GPU, you basically increase the throughput. So here the x-axis is basically the number of data points for each batch, I believe, or they double it. And so basically with multi-head attention, you can fill the GPU up to a certain point, but then it's you run out of memory. And with these other methods, you basically can keep adding batches or elements to the batch and therefore increase the throughput. Cool. Limited context length. I also heard this today. I will make this short because this is a fairly common issue. Lots of people have been talking about and lots of papers have discussed this. So perhaps one interesting distinction is, can a model deal with longer context at all? And can a model deal well with it? So for example, with Llama 7B, there is not much that hinders you to feed in larger context length inputs than it was trained on, but the perplexity will explode fairly quickly. And so this paper compared with fine-tuning the model on longer context inputs, which did help significantly, but still could perhaps be improved. And so one idea is position interpolation, which works if you have rotary positional embeddings, where the position index can be a floating point number. So the idea is like basically exploiting this observation. The idea is that instead of extrapolating to larger positioning indices that you have seen during pre-training, which is done here in the first row, you can just squeeze your position indices to numbers that are not integers, and thereby increase the context length by then the model having interpolating between these floating point numbers. And this works incredibly well, surprisingly. So they, for example, take, again, like a 7B model, which I think was pre-trained on like usually something like yeah, like 2048, and then they fine tune it on, for example, 8K, and then they see that, first of all, even for smaller contexts, it still doesn't really degrade the performance. So this is perplexity here, so lower the better. And it actually makes the performance better on smaller context lengths than it's fine-tuned on, but it also allows you to decrease the perplexity on much longer context lengths. Another challenge perhaps to raise here is based on this recent paper, Lost in the Middle, where one idea, for example, for increasing performance for downstream tasks is to just try to retrieve as many documents as you can, given your context length window, and then hoping that all this information is better than having no information in the context. But this paper showed that sometimes, even if you retrieve relevant documents, but you put them, for example, in the middle of the context, this will decrease the performance compared to having no example in the context whatsoever. So basically, the purple line here is the open book performance, where open book means you add the retrieved examples to the input and you have the most relevant examples in the middle, like at the 10th position of these 20 examples. But this can, basically even underperform just the closed book setting where you don't add them. Okay, cool. I think that's the last one on my side. So hallucinations, we also had this already, Julia code written that doesn't really exist. We argue, based on also previous work, that one framework to think about hallucinations is that there are intrinsic and extrinsic ones. So intrinsic means that the text that is generated doesn't really follow the input context. So it basically just contradicts the input. And extrinsic is more along the lines of the input might be underdetermined, or you might want the model generate something that is not easily verifiable by the data you have, and the output is seems still nonsensical. So around the time when we wrote this survey, we played around with ChatGPT and GPT-4, and we, for example, asked it before we put out our paper, which papers discuss challenges and applications of LLMs, and it reported these 3 papers. The first one is indeed the GPT-3 paper, but the second and third one doesn't really exist. And it's kind of interesting because the authors that they mention, at least in the second row, Jacob Devlin is a really famous author. It's the first author of the BERT paper, for example. So it seems like it kind of understands, okay, like you asked me about language models, I will just use like famous authors in that realm, and this might be correct. Yeah, this is like a classical hallucination. This was like first try, by the way, it's like not cherry picked or anything. And around that time, web browsing was still a thing. They turned it off recently. Yeah, we tried to let it browse the web. It did retrieve relevant documents, so I checked them, like these papers did exist. But then again, like the first document was correct or correctly summarized, but the second document was really, non-existent. So I think the reason why we highlight this is because retrieval is often mentioned as like kind of like a silver bullet to reduce hallucinations. And I would argue that it can help a lot, but it's not always as easy as like, just having some KNN and some big database and it will, resolve everything magically. In the paper, we make this distinction following previous work. We also categorize methods that try to solve these issues by either decoding strategies or more sophisticated retrieval strategies. To give you one more concrete example, one idea I really liked is this idea of demonstrate, search, predict. So in this paper, they argue that, again, like you ask the vanilla LM about a question, it hallucinates, you give it access to a retrieval database that in theory has the right information, but the data is not stored in a way where it's like a one-hop answering or like a trivial recall of a fact and that's the answer. It's more like it requires a multi-hop reasoning. And so it's still like retrieves a different building in that setup. But their approach, which I will cover in a bit more depth on the next slide, allows you to first decompose a question into multiple relevant sub-questions and then answer these sub-questions using retrieval, and then predict the final answer. So in a bit more depth, imagine you ask this question, how many stories are in the castle David Gregory inherited? And your database, you don't have like an exact question answer pair for this. So you give it a few general question answer tuples, like a here 2-shot training example in the prompt, or yeah, in the input for this method, demonstrate, search, predict. And so the method first tries to decompose these questions in different ways that still would answer in the correct way. So you can imagine this to be a bit like augmentation of the training few-shot examples. And if, for example, one question answer pair seems incorrect that was generated, it will be discarded. And given then this new prompt, you try to retrieve again from the database with these like multi-hop question answer pairs. And then based on that, you know, let the model in the end predict the final answer. And this seems to work pretty well. So again, compared to having no retrieval at all, it's a big increase, but even compared to either vanilla retrieval or similar retrieval methods that have been proposed more recently, like self-ask, it's still a big gain. Cool. Yeah, that was from my side. Any questions to whatever I just talked? Otherwise, I would give the stage to Joshua. No? Okay, cool. Thank you.
John. Hi, everyone. So can everyone hear me okay? Awesome. So I'm going to talk through some of the key takeaways from the applications section of the paper. I think the first thing to note is that there's lots of applications. I think that's going to shock everyone. In the paper, we look at things like law, robotics, reasoning, etc. I'm not going to go through all of these today, so if you are interested in sort of a brief overview of any of them, do go have a look at the paper. What I want to talk about today, though, and related to Jean's talk, is how the challenges we discussed in the paper are starting to spill over into more complicated application architectures, with people trying to solve the problems of LLMs as they are today by adding in traditional software around them into ever more complex degrees, and how successful they are in different domains. So I think the first thing to say is that obviously standalone LLMs, and by that I mean an LLM that takes a raw user input, generates a raw output that you provide back to the user as the answer to that query, can solve, as we can see, a whole range of tasks on their own. What you see in the literature, though, is increasingly the cutting edge applications are coming up against those challenges that Jean discussed and really hindering what you can do with a standalone LLM on its own. And I think there's 3 challenges particularly that are doing this. The first is, as Jean's mentioned, the limited context windows. And you can see that in code generation. So a big issue there is that lots of papers highlight how, without being able to access the wider repository context, you can really limit how successful any code generation model can be when it's deployed in the real world. Creative writing. So similarly, LLMs are obviously very good at creating short stories, etc. As soon as you get to anything long form, multi-thousand words novels, they become a massive constraint if you can't fit the previous history into the context. Similarly, knowledge work, if you've got a 1,000 document legal case and you can't obviously fit them all into your 100K, you then have a massive problem when you're doing any sort of legal question answering or knowledge work with that. And finally, genomics. Short genomes, protein language models are being very successful. Once you scale that up to, say, the human genome, they're vastly too short context windows to fit into your into the transformer, and that again hinders what you can do in genomics. The other 2 are hallucinations and outdated knowledge. They are much more focused in sort of more professional domains. For example, medicine, where because it's a safety critical application, you find any hallucinations massively hinders how you can deploy it in the real world. They even flags in sort of MedPalm 2, they say that much more work is needed before you could deploy this. And similarly, in law, the big issue is potentially outdated information, where rapidly changing laws and precedents, for example, as soon as Brexit hit in the UK, which massively changed lots of statutes, you'd need to massively retrain your model, but otherwise it would have a huge amount of outdated knowledge in it. And finally, chatbots. The previous two, you can kind of get around some of the issues of hallucinations and outdated knowledge because the people using them are potentially experts and can identify potential issues or filter out problematic results. If you're dealing with non-technical users that potentially don't know whether the output is harmful or incorrect, again, you have a higher standard that you need to pass for hallucinations and outdated knowledge. And I think what's interesting then from the literature is that the people are trying to get around those challenges in a whole variety of ways by building software architectures around them. The sort of lowest level of complexity is just to go for a more complicated or advanced prompting strategy. We go into a number in the paper. I won't go into them here in detail. But I think the interesting thing, though, about prompting strategies is they only really deal with the intrinsic hallucination problem that Jean mentioned, in that if the model has the knowledge, but it's reasoning about it incorrectly, then prompting strategies can be really successful. For example, self-consistency, where you generate a whole range of answers and then pick the modal answer to add essentially a sampling strategy to solve potentially intrinsic hallucinations. The problem is it doesn't solve the other problems. Outdated information is if you can do whatever prompting strategy you like, but if the model has the wrong information trained on it, it may well still give you hallucinations or provide outdated knowledge. Similarly with context length, if you can't fit your entire legal case into the context window, the model can't hope to necessarily provide you the correct output and might make up the missing data. And finally, with extrinsic hallucinations, a prompting strategy, if it doesn't have the information available to it, can't solve it without some forms of other retrieval augmentation. And so I think the real thing to say is the prompting strategies only get you so far. They can be very successful, but definitely aren't a solution to all of the problems in these applications. That leads us up to sort of the next level of complexity you can see in the literature. And then these are single prompt architectures. So we talked about a single input prompt and a single output. And this is where you have a traditional software module, sort of LLM plus X, that you add on to your LLM to try to solve some of these challenges. The most common, as Jean's already mentioned, is retrieval augmentation, where, for example, in coding, RepoCoder, you first get your model to predict an output, you then search over your code base for relevant bits of context, relevant bits of repository context might be useful, and then input that into the prompt to refine the output. Similarly, with ChatDoctor to solve hallucinations, you can add on a medical database or Wikipedia that you can include in the prompt to reduce the risk of harmful medical hallucinations for your medical chatbot. The second one, which is also common but less so, are resolvers and grammars. And that's more about refining the output, where you take an unstructured, for example, in this case, this is a paper where you're trying to extract medicines from medical notes, and you add on traditional NLP techniques to refine the unstructured LLM output into, say, a list or a JSON, and although GPT-4 is getting increasingly good at this off the bat. And the other example would be context-free grammars, where you do constrain the sampling strategy to only produce the type of structured output that you're looking for. And those can be really useful if you're looking for sort of predefined set of output structure that can really solve your problem. The third, and I think actually surprisingly common to me, and you see in the literature a lot, is an API approach, which both deals with hallucinations and context length at the same time. If you first define an API, so you don't give the actual code implementation, you just define what each function does and include that in the prompt, you massively cut down how much context you need to contain your code repository, and you also reduce the risk of your model hallucinating anything of any of the implementation that you've already got, because you've separated that out from the model. And examples of that would be ViperGPT with visual language processing, where you give it an API that defines low-level visual tasks, like finding an object in a picture, and you then allow it to use that API to answer higher-level visual queries. And similarly in robotics, with ChatGPT, you first develop a low-level robot, say motor control library, and provide the definition of that to ChatGPT. It then uses that to solve the low-level robotics task without ever having to need to know what the robot needs, what the low-level robotics control implementation is. The final sort of module that people often add on, and you can see in the literature, is discriminators. And so this is more about adding additional smaller models to either filter prompts or filter outputs. So for example, in the repo level prompt generator paper, they first propose a number of prompts that contain repository context, have a classifier that decides which prompt is the most relevant, and sorry, which prompt proposal is the most relevant, and then uses that to generate the final output. Whereas for creative writing and detailed outline control, they have a model that controls the sampling of the output such that it, for example, maintains coherence more effectively than the original LLM. Those, though, unfortunately, still don't solve everyone's problems in these applications, and that's when you start getting into these much more complicated multi-prompt architectures. And I see sort of two varieties of this, I think, in our paper. The first is a hierarchical architecture, where you essentially decompose a much longer task into a series of subprompts, potentially with post-processing steps in between. And this is really common in creative writing. For example, Dramatron and RE3, where they try to write very long-form stories by starting and saying, first, write me the outline of this story as high-level sections. They then have a prompt that says, break down that section into key characters, plots, etc. And a third prompt that then actually writes the infills those paragraphs and trying to maintain a coherence across them. And you can get into some very long sort of hierarchical prompting pipelines to try to solve these tasks. The other example of multi-prompt architectures that's quite common is these recursive feedback architectures, particularly in coding with things like self-debugging, where you might get your model to first generate an output, and then to explain the output and why it might be incorrect, and then use that second prompt as a recursive input to then refine the output again. And you also often do things like unit tests as well that you can include in the input. Similar things can be done in robotics in the Reflect paper, where they basically use the LLM to describe what it thinks has gone wrong when it's doing the robotics task. The final level is then agent architectures. And we don't go into these in detail in the paper, but then you basically strap all of these together to try to create a semi-autonomous agent. And I'm sure people are familiar with these. This is the Voyager example, which is a Minecraft playing agent. And you've got, firstly, hierarchical prompting as part of an automated curriculum. You've got a skill library, which is essentially a retrieval system, but that skill library is defined as an API that you can add new skills to through another additional prompt to write a new skill. And then you can retrieve those skills and then iteratively refine the code if it's failing through a sort of self-debugging approach. And so this really shows how you can combine all of these sort of traditional software modules around an LLM into something that actually can sort of autonomously play Minecraft. These are getting fairly complicated though. I think that leads me on, oh sorry, no it doesn't actually. That leads me on though to my next one, which is multimodal architectures, where you start to actually include additional modalities as pre and post-processing steps. And to be clear, I don't mean a multimodal model itself. I mean where you're adding on an additional pre or post-processing step where you're converting something into text or out of text that can then be used by a different modality model. In the pre-processing example, you, for example, might take a picture of a chart, have a image to text model that converts that chart into a tabular data that it thinks represents the details of that chart, and then provide that tabular data to the LLM to provide the output. And that's what dplot essentially does. The other very common examples where this appears is in robotics, where you have this pre-processing step to convert a variety of sensor data into text to describe, for example, the scene in a room, which can then be used by the LLM to describe what might have gone wrong if the robots failed. On the post-processing side, you flip, obviously that, and you get your LLM to potentially produce either code or some structured format that can then be used to condition, for example, an image model. An example of this would be Layout GPT, where you first prompt your LLM to, for example, give you the layout of a picture. Say I want 2 cats in the top right-hand corner, and it will give you bounding boxes and descriptions to reflect how that picture should be structured. And you can then use that structure to condition your image model to generate that output. These, though, I think are obviously getting around lots of issues of multimodal models, and whether they will last, whether they will scale, I think it remains to be seen. And so I think there is a much broader question here, and kind of the reason I've gone through these different levels of complexity is that in the literature you can see these ever more complicated architectures coming out, and they're in many ways creating lots of their own problems, whether they're not that robust, whether they're hard to evaluate. And I think that is whether there's a limit to this, whether we're going to scale complexity or whether we're going to improve the underlying model. I think is the kind of one of the big questions in the applied area at the moment. This is the most complicated flow diagram I could find, I think, from SAPLAN, and you can see the LLM is becoming a much, much smaller part of the overall flow. And this is for planning in a 3D environment, I believe. And I think the question is whether we're then going to replace that essentially with a better model over time, or whether we're going to increase the complexity. That is it from me. So I just very quickly summarize. I think there's obviously a lot of challenges that Sean's gone through. There's many more in the paper. These challenges are currently quite a big constraint, I think, on the state-of-the-art applications. And I think that we can see that coming through in the complexity of the software architectures we're seeing around them. Whether that will scale, though, remains to be seen. I'll leave it there and potentially take any questions.
Thanks so much.